Hi everybody, back to problem fusion webs in communication electronics. For this series, going to be on the chapter 7. Okay, for the problem 7.6b, evaluate the constant C1 and C2 in the logarithmic transformation so that U represents the potential function involved about a line chart of strength QL coulomb per meter. Let potential be 0 at R equal to A. Okay. So about the problem is want you to apply a logarithmic transformation to the problems, and you have a line chart of strength QL. So we are going to do a transformation. You can see that let's review the logarithmic transformation in the circular boundary logarithmic function. You start from W, which is the equal to the real part and imaginary part, U plus JV, and that's the equates to C1 ln Z plus C2, where your Z in the form of R exponential or J phi. It's like Euler's formula, right? That's from equation 7.67. So by plug in your Z in W, you end up with W equal to this term. So this has become the real part, that's U, and your theta C1, that's become imaginary part, that V. Then this is the U actually is the potential term that's going to be equal to C1 ln R plus C2, where C1 and C2 are constants. That's from equation 7.69. And your V, that's from imaginary part, equal to C1 theta. That's from equation 7.610. Now, they give you the boundary condition, or the conditions that the potential will be 0 at R equal to A. So this is your potential. At R equal to A, U equal to 0. So that means you represent R by A, and that's give 0. So you end up with C1 equal to negative C1 ln A. Then from U equal to C1 ln R plus C2, you know the relations between C1 and C2. So you have U become C1 ln R for A. That's your potential at any particular distance R. Now let's consider the line chart of the strength QL equal to coulomb per QL coulomb per meter. And you know the definition of potential is just the negative line integral of electric field dl. And your ER equal to the charge density divided by 2 pi epsilon in the case of the line charge. So you just do integration, you end up with negative QL over 2 pi epsilon ln R over A. So they both represents the potential, and but this one is from transformation method, right? So by comparison, you can see that this is your Q. This is your C1, going to be your negative QL over 2 pi epsilon. Now, somebody probably, let's review back why your ER for the line chart equal to QL over 2 pi epsilon R. Let's go back to Gauss' law. You have the line chart, and this one you make the closed surface integration. So that's going to be equal to Q enclosed, right? And D in dr and your ds. This is the surface, the closed surface. Since dr has only r direction, so you can ignore. Actually, this one is going to be 0. I mean, at the lids of a cylinder. And the area going to be 2 pi r multiplied by the length. That's become the surface. And for Q enclosed, simply equal to the line chart density multiplied by the length, which is L. So that's why you end up with your ER equal to QL over 2 pi epsilon r. That's we have right here. That's the problem 2.6b. Next one is the 7.6e. Apply the results of the inverse cosine transformation of item 4 in exercise 7.6c. Take the right hand semi-infinite plane extending from x equal to a to x to infinity at potential v0, and also take left hand semi-infinite plane extending from negative a to infinity for x at potential 0. Then also evaluate the scale factors and additive constant. Okay, let's take a look. You have the semi-infinite plane. So you have one plane at a and extending to infinity, and the other one is there at x equal to negative a and extending to negative infinity. The inverse cosine transformation or hyperbolic and elliptic conducting boundary, and for x extending from a to infinity, you have the potential become v0, and from negative a to negative infinity, that your potential is 0. So let's apply the inverse cosine transformation. You have W equal to U plus JV. That's equal to inverse cosine of Z. And your Z equal to X plus JY. Or from this one, you can write cosine W equal to Z, right? And since your W equal to U plus JV, you can expand the cosine term, or cosine A plus B equal to cosine A, cosine B minus the sine A, sine B. Let's transform. So for the problem, we're going to create a new plane, which is the W prime. You already have our W here. So your W prime actually equal to C1 inverse cosine KC prime plus C2, where K is the scale factor and C2 is the fixing the reference for the potential. So that's the correction term. Both C1 and C2 are constants. Okay. So your W prime, since your Kc prime equal to Z, where K is their scale factor, you end up with W prime equal to C1W plus C2, or equal to U prime plus JV prime. Okay, and this is your W. And then you know that your prime is actually the real part, which is the C1 U plus C2 and V prime, the imaginary part. So that's the C1 phi. Now let's do the problem by applying boundary. This is the boundary condition. You have to look back of figure 6.6, 7.6e and F, page 341 and 342. For U equal to 0, and this is the transform plane, U prime equal to V0. And also for U equal to pi, that's give you U prime equal to 0. And with the scalar factor Kz prime equal to Z. So at Z equal to 1, Z prime equal to A. So this is your scale factor K equal to 1 over A to map two planes. Since you already have the relation between U prime and U prime actually C1 U plus C2. So by applying the boundary conditions, you end up with C2 equal to V0, and for U equal to pi, U prime equal to 0, you end up with C1 equal to negative V0 over pi. Now you can write W prime in the term of the U, since you already know the constant C1 and C2. And that's give you W prime equal to V0. Multiply these expressions, that's their cosine inverse. And since your potential is actually the real part of W prime, which is this term, C1W. So you end up with phi equal to V0 multiplied by 1 minus 1 over pi, the real part of inverse cosine of Z. Okay, so this problem is about the inverse cosine transformation. (7.12a). So we are working a lot on boundary conditions for different type of problems in the term of the potential. Obtain a series solution for the two-dimensional box problems in which sides at y equal to 0 and at y equal to b are at potential 0. So y equal to b and y equal to 0, you have the potential 0. And in planes at x equal to a and x equal to negative a are at potential V0. This is your x equal to a, negative a, and this one are at x equal to a, you have potential become V0. That's the boundary conditions. Okay, you need to look back in the textbook from section 7.9, page 352. Your phi xy equal to these expressions, or equation 7.98. What you need to do is you need to apply the boundary condition and get rid of some constant sorry, are some term that you don't need it. Okay, look at the system. By applying boundary conditions, you start with v equal to 0 at y equal to 0. This is your y equal to 0, right? You pick up this equation. So for y equal to 0, you have y here from equation 7.98. Sorry, I'm missing something here. That's supposed to be your cosine kx, and this one cosine hyperbolic psi kx. For y equal to 0, you go to this term. So that's the become cosine 0, and this should become sine 0, which is equal to 0. But cosine 0 equal to 1, not equal to 0, but you want this term to multiply this term and end up with the potential to be 0 as they're specified by the boundary condition. So C has to drop, or C equal to 0. That's the first boundary condition. The second boundary condition, at y equal to b, the potential also 0. So since from equation 7.98, you don't have this term anymore, right? By applying the first boundary condition. So at y equal to b, you keep leave this term, but this there you plug in y equal to b. To make the potential equal to 0, that means this term has to be 0. But d is not equal to 0. So psi kb has to be equal to 0. That means your kb has to be equal to n pi. And that's give you k equal to n pi over b. Let's move to the third boundary condition. At x equal to a, you have potential become v0. So you represent phi a y equal to v0. X equal to a, and you just leave y as it is. So your v0 equal to this term. Can you do anything? I have equation, I applied the boundary v equal to v0 at x equal to a, and also I have v equal to v0 at x equal to negative a. But you take a look at these two terms, hyperbolic psi ka and hyperbolic psi negative ka. You can sorry, since you need a potential to be v0 for both cases, you cannot have this term, right? Because they have a different value. So that means your b has to drop, or b equal to 0. So you end up with your phi xy going to be only a term, and what? The term, right? So you have phi n xy equal to a hyperbolic cosine kx multiplied by d psi, sorry, this is not supposed to have h, just like psi ky. Now at x equal to a, your potential also equal to v0. from potential equation, you have a phi n xy equal to this term. That's equal to v0 at x equal to a. So you have x equal to a. So you have a phi n ay equal to this term. Now from equation 7, 11, 14, since you see this expression, you can expand this one into Fourier series. And from equation 7.1114 at a, your fx equal to these expressions, or fx equal to the sigma of n is odd number to infinity. You can see that this is the half-wholly odd number, come like nx. You start from 1, 3, 5. Okay, this is n pi x over a. And from the denominator, so you have this become I'm sorry, for the coefficient you have 2 over 1, 2 over 3, 1, 3, 5, and so on. So you need to divide it for c by n, and you also have pi. So that's why I have this term. You have x equal to summation n odd number to infinity for c over n pi psi n pi x over a. Okay, this is your fx. And if you compare to the potential, you also have a psi term. So you see simply equal to what? Going to be equal to v0. And what else? Your k, your a simply become b. You need to go back to the previous page. Because here you have k equal to n pi over b. But from equation 7.1114, you have this one become n pi over a. And then you can write your Fy equal to this expression. Then your for V0 over n pi, that's going to be equal to this term. And Cn, right? Because you compare two equations. And that means your Cn equal to for V0 over n pi divided by hyperbolic cosine Ka, or your sine n xy simply equal to okay, sorry, let's start over again. This is your phi n xy. That's going to be for your Cn. This is your Cn. So this becomes your Cn. And then multiply by hyperbolic cosine n pi x over b. And multiply by psi ky, or n pi over b. Okay, so it's just this is how we get start for the Fourier series. Fx equal to summation bn psi n pi x over a, and you can look for bn by integration of function multiplied by psi. Okay. problem 1.4c, similar to the previous problem. Or the problem 7.12a. But this one is just become the plane extend to infinity instead of to a as the previous problem, right? What I want to note is that for infinite plane, you apply exponential functions. That's going to be much more convenient for you to solve the problem. Why? Because for since you know x go to infinity, and for the exponential term, some terms are going to drop, right? So that's why we use the exponential function. That means your potential as xy going to be a psi ky plus b cosine ky, and multiplied by c exponential negative kx plus the exponential kx, and you follow the same steps to solve the problem by applying the boundary conditions. 1, at y equal to 0, your phi or your potential is equal to 0. Let's take a look at this one here, earlier y dependent. So sine 0 equal to 0, but this one is equal to 1, I mean cosine 0, and that's equal to potential equal to 0. So you cannot have b. This term have to drop. Again, for y equal to b, your potential equal to 0. So I'm missing some term here. This is supposed to be we have this term, right? B equal to 0, so you're supposed to have this term a and psi kb, okay, and my multiply by x dependent term, and you have kb equal to n pi to give to make the potential equal to 0. So your k equal to n pi will be. Now at x go to infinity, sorry, for x dependent term, you cannot have d, because this term will increase, and that's impossible. I mean, that's not allowed. So d has to drop. So that's why we have d equal to 0. This term are going to drop anyway for x equal to infinity. So you end up with what term? You have only a psi ky and c term. So become cn psi ky exponential negative kx. You do the same thing by applying equation 7.11. It's just your job is to do a Fourier series. Okay, so you can look back at the previous problem, and you end up with your phi xy equal to this expression. You have only psi term and exponential negative x term. Okay, that's all for this series, and I think I have two more series, to go before I finish, everything. Okay, bye.